Welcome. So, good morning, everybody, or just barely after lunch. Um, Today's speaker series is Potash 101, Understanding the Industry and the Innovation. I would like to take a quick moment to do our land acknowledgement. We acknowledge in Saskatchewan that we are in treaty territory, specifically Treaty 2, 4, 5, 6, 8, and 10, the traditional lands of the Cree, Saulteaux, Dakota, Dene, Lakota, Nakota, and Métis Nations. We recognize and honor the rich history and contributions of Indigenous peoples to these lands and commit to moving forward in the spirit of reconciliation and respect. We encourage you to strive to be allies for Indigenous peoples and reflect on the lands where you are situated and seek to learn the strength, resilience, and achievements of Indigenous peoples. My name is Carla Wagner. My pronouns are she, her, and I am a DCS technician with Nutrien, and I volunteer with Win-Win Saskatchewan, and I'm your moderator today. We ask that everybody keeps their mic on mute. Feel free to have your cameras on, though. It's always nice to talk to people's faces and not to darkness. And feel free to put questions in the chat. We'll be monitoring, and if there's time, we will hopefully get to answer some of them. The session is recorded for future reference. And today's event, the summary is, Potash plays a critical role in Saskatchewan's mining sector and global food production. Join a session that explores the fundamentals of potash processing, the technologies behind it, and how innovation continues to shape the industry. Walk away with a clear understanding of how processes evolved from concept to operations and the role collaboration and continuous improvement play in advancing mining practices. So our speaker is a fellow Nutrien employee, Chantel Coburn. She's a senior process innovation engineer with experience in potash processing technology development. Her work focuses on process optimization, pilot scale testing, and advancing innovative solutions from concept to operation. She is passionate about collaboration, mentoring engineers, and driving meaningful innovation in the industrial operations. Take it away, Chantel.
Hey, thank you for the kind introduction, Carla. I am going to attempt to share the correct screen for when I
believe in us.
I know, holy.
I am seeing a screen with a bird.
Okay, now you should be seeing Potash 101.
Yep.
Okay, amazing.
Perfect. I'm going to throw myself on mute, and as again, if everybody else can just keep their mics muted while Chantel is going through the presentation, that would be great.
Perfect. And apologies again. I don't know why we don't have our camera working, so you'll just have to imagine what we look like in the background. So it's Jenny and I who are going to be presenting, and I'll just tie this into a quick little safety share. So yesterday, it was my son's 8th birthday. We were at the beach, and there was a water bomber practicing. So I was scooping down into the water, picking up water, and then dumping it just over and over again at Blackstrap. And the first time, like, wow, that's so cool, kids. They're practicing to be water bombers. And this one person at the beach so confidently said, no, they are stocking the lake with fish. All ecosystems in Saskatchewan, or lakes in Saskatchewan, can't support fish ecosystems, and they have to stock them. And said it so confidently that I think you might have believed them if you didn't use a little bit of critical thinking. So how this ties in is I had to recruit Jenny to talk about the underground portion of Potash 101, or else I would have to be pretending to be confidently talking to you about underground mining. So there you go. A little about me, Chantel Coburn. I am a senior process innovation engineer at Nutrien. And really my job doing that is to find new and innovative ways to improve potash processing. So that can be really a number of different things that kind of encompass a few different things, looking at ways to reduce our environmental footprint, improve safety to our operators, reduce the cost of potash that we make, or increase our production. And that's kind of the work part of me. And then the 51% of me, I guess, is the fact that I have 2 little kids and a boatload of animals. So there they are with our new chicks. Now I'll pass it over to Jenny.
Okay, thanks, Chantel. Yeah, so apologies if the listing or the posting tricked anyone to joining. So you're going to have to sit through mining as well as processing. So if you're not here for mining, I guess maybe turn your speakers down for 20 minutes until Chantel comes back. So my name is Jenny Scott. I'm a manager of our mine development team here at Nutrien. I also volunteer with the Win-Win group. Like Chantel, I also have two kids. I said a boat, but not a boatload of animals. So there are my children in the boat. And our team, so we basically enable safe and efficient potash operations by providing geotechnical and mine engineering support. So we work with all of our Nutrien potash and salt mines in areas of geotech and mine eng. So things like ventilation, ground control, inflow, shaft liners, planning, all sorts of different areas. Okay, so today, a bit of for the agenda, we're going to talk about what potash is. This is going to be very like Potash 101. So if you're an expert, you'll probably know some of this already or know all of it. So we'll talk about what is potash. We'll talk about the geology of Saskatchewan and how we got the potash that we have here. And then we'll go into the mining 101, and then Chantel will take over and talk about processing. So to start us off, what is potash? Potash is a generic term for a variety of mined and manufactured salts, all of which contain the mineral potassium in a water-soluble form. So it's a very sort of generic thing, but what does potash mean in Saskatchewan? Really, what our potash here is made up of is about 40% sylvite, 55% halite, and then 5% insolubles. So 40% sylvite, that is the potassium salt, and that is what we want. So that's what we're trying to mine. We want to get that potassium. And so that makes up about 40%. The 55% halite, this is just regular old NaCl or table salt. So the stuff you put on your French fries, we've got 55% of it in our ore body. And then the remaining about 5% is what we call insolubles. So often we'll refer to these as clays or clay seams, but they're not actual clays. They're insolubles. So they're fine-grained anhydrites, dolomites, quartz, and other kind of fine-grained insoluble minerals. And then we do have a little small percentage of carnallite. Carnallite is a magnesium-bearing salt. It's considered an ore contaminant, so the mine doesn't like carnallite, the mill doesn't like carnallite, so we try to avoid carnallite if we can, but we do sometimes get a little bit of it in our potash mines. So there's about a 3-to-1 ratio of raw ore to finished products. So what that means is when we mine the potash, so you just saw we have more halite than sylvite. So when we actually bring raw ore to surface, for every 3 tons that we bring up from the mine, we end up with about 1 ton of finished product. So the rest of I guess the 2/3 of it end up going to that beautiful pink tailings pile you see there in the lower right of the picture. So when you're driving through Saskatchewan, you'll see lots of these pink hills, I guess, near our potash mines off the highways. If you see those, they're basically salt for the most part. And of course, what is fertilizer? So I talked about us wanting to get that potassium out of the ore or out of the what we mine. So the potassium is used for fertilizer. There's a few different uses, or quite a few different uses of potash or potassium, but really the main thing is fertilizer. So fertilizer is obviously plant food. We feed our crops with it. We grow strong crops because of the nutrients we put into the soil from the fertilizer. And so there's 3 main nutrients in fertilizer, nitrogen, phosphorus, and potassium. So where our potash mining industry comes in is that potassium piece. Okay, so we know what potash is, we know what it's used for, but why is it here? And so the really cool thing with Saskatchewan potash geology is that we have the best potash deposit in the world. Right here in Saskatchewan. So right under all of our feet right now, we have this world-class deposit. So why do we have this deposit? How is it here, and why is it so great? So about 360 to 390 million years ago, the Earth or the world didn't really look how it did. Our continents weren't in the same spot. So if you think back to your high school or elementary school days, if you remember the term plate tectonics, there's plates that move around. And so things aren't where they things aren't where they are now, where they used to be, I guess. So 360 to 390 million years ago, Saskatchewan wasn't where it is now. And really it was located right near the equator. And that when potash formed, I guess. So it was located near the equator in a marine basin in a very arid climate. So if you think about when you go on a hot holiday near the equator, what does it look like? Often there's an ocean. Often it's hot, it's sunny, right? And so this is a very important piece to how our potash formed. So basically, I know you weren't here for a Geology 101, so this is pretty high level, but basically there was a bit of a lagoon or a low-lying inland sea where Saskatchewan was, and it was hot. So the water evaporated and ended up leaving behind it potash and salt deposits. There's a bit more to it. There was a reef that was in the northern part of the basin called the Presqu'île Barrier Reef that basically restricted the influx of fresh water into that kind of lagoony, low-lying sea. But basically, shallow waters, intense sun, evaporation leads us to this amazing deposit called the Prairie Evaporite Formation. So it's about a 200-meter thick deposit of salt and potash. And here's just a figure of the potash basin in Saskatchewan. So anywhere you see pink is where there's potash. The potash is about 1,000 meters or a kilometer below us. So if you're standing in Saskatoon right now or in Regina, you have potash below you. In Regina, it's a bit deeper, I guess. But if you're in the Saskatoon area, it's about a kilometer. And then you can also see there's red and blue dots indicating some of the potash or all of the potash mines in the province. When we look at the geology from surface to underground, there's a few important things here. So I guess the first is where that red line is pointing. So about 1,000 meters down, that's where our Prairie Evaporite Formation is. So that's that salt deposit, and that's where the potash is. But I also want you to note about midway down, there's, I don't know if my pointer will work, probably not, but about at the 500-meter mark, there's a sandstone formation. So that's a formation called the Blairmore Formation, and that's a really important piece of geology. There we go. Thank you, Chantel. So right here, this is a very important formation to note about midway down to the potash in terms of sinking shafts. Okay, so you know where the potash is. How do we get to it and how do we mine it? So how do we get underground? So when you drive to our potash sites in the province, you're generally going to see two tall buildings, and these are our shafts. So you'll always see a smaller shaft and a taller shaft, I guess. The bigger shaft is the production shaft. So on here, it's called shaft 1. So that's where we're bringing all of our potash ore from underground up to surface. And then the other shaft is used generally, well, pretty much for everything else. So it's called our service shaft. So basically, people and material go up and down that shaft, as well as we push air down ventilation. The ventilation goes down one shaft and up another, so it depends on what site. The setup's a little different, but generally speaking, people and materials go down the service shaft, and ore comes up the production shaft. And when you think about, so our underground mines are quite big. They're kilometers and kilometers long. We've got big shops. We've got big mining machines. We've got vehicles that people drive around. And so when you think about, you know, a shaft or our mines, these are the only ways to get into the mines. So if you're talking getting equipment underground, like a big borer, that has to go down the shaft. So if it's too big to get down the shaft, we actually disassemble a borer and take it down part by part down the shaft, and then we reassemble them underground. So quite a process to get big equipment underground. Okay, I wanted to put a couple slides on the shafts themselves because this is important, the construction side of things. So how do we sink a deep shaft, 1,000 meters deep, when they're such a critical component? So if we didn't have our shafts, we wouldn't have our potash mines. And interestingly enough, so I pointed out that Blairmore Formation a couple slides ago. So that's an important formation because that formation is, like I said, a sandstone formation. And basically, if you were to go to that formation and scoop it with a shovel, it's essentially beach sand. It's an aquifer, it's full of water, and it's like loose, unconsolidated sand. So something that's very, very difficult to sink a shaft through. And in fact, the first potash shaft ever attempted was in Saskatchewan, was in the Unity area. And because of this formation, basically they got as deep as that formation, it flooded the shaft and they just couldn't get control of it and they lost the shaft. So we don't have a shaft there or a mine in that location because of that. So after that, we had to get smarter and figure out how exactly do we mine through these formations to get to the potash. So this picture is a picture of our Scissors Creek shaft. This is our newest shaft at our Nutrien-Rocanville mine in the southeastern part of the province. This is before the shaft construction, I guess. So this is basically, if you look at all of these little, sorry, I'm trying to find my cursor again, all of these pipes sticking out around the diameter of what will be the shaft, those are called freeze holes. And so basically, we have to freeze the ground in order to sink through it. And really what we're trying to freeze are those aquifer layers. And the most important one is that Blairmore Formation. So we freeze down, those pipes go a little bit deeper than the Blairmore. We freeze that ground so that we're able to sink a shaft without flooding the shaft as we go. This is the inside of what our shafts would look like. So the picture on the left is a concrete liner, and the majority of our shafts in this province are lined with concrete liners. Some of the potash shafts do have steel, but most of them are concrete lined. And then on the right, what those steel or those cast iron pieces are called, basically that's tubbing pieces. So those are made out of cast iron and they're put together and sealed by lead. So those cast iron tubbing pieces are basically these rings that go in at the aquifer locations. So at the Blairmore Formation where we froze, we would install these cast iron rings, and this is basically what prevents our shafts from flooding and basically withstanding the pressures of these water bearing formations essentially. So fun fact about those cast iron tubbing rings, there is a display at the Western Development Museum as well as at the Saskatoon Airport in the baggage carousel location in that area. There's actually a little display that explains these rings and talks about them. So pretty cool innovation, and without these, we wouldn't actually be able to sink our shafts in the province. Okay, so once we get our shaft, then we get down to potash level. So this is what a typical mine might look like as you're coming down into potash level. So on the left, you can see the shaft, and then on the right, it's actually looking out of the shaft. So you can see that it's pretty wide open. A lot of people who don't know potash mine expect really kind of small, tight spaces and expect to be claustrophobic, but it's a lot more open than people expect. Like I said, we've got kind of full travel ways, full vehicles cruising around down there, and it's kilometers and kilometers long. So they're quite large. Okay, so we've made it underground. Now we're going to talk about the mining process. So when we mine, we do something called retreat mining in our potash mines. And what that means is we basically mine to the furthest extents of our mines, and then we work our way back. And so the pictures I'm showing right now are basically at the active work face, which would be kind of the furthest extents of the mine. And the reason we do that style of mining is because we want to make sure that we are preserving all of our long-term travelways as best we can. So if we were to mine one not that far out, but close to the shaft and start doing a bunch of mining around it, we would actually impact our travelways and they would start to deteriorate on us. So it's very strategic why we do this style of mining. But in these pictures, we're at the active mining phase. So this would be kind of the furthest extents of the mine where the borers are actually mining out to get the rock. So the picture on the left is a picture of a typical mining machine in our potash mines. So this is called a continuous miner. You can see there's an operator working under a canopy on that machine. And in this case, he would be cutting kind of into the screen to the right. So the front of you can see the front of the machine. Sorry, right around here, if you can see my cursor. And this machine would be going into the screen. So if you look at the picture on the right, that's what the front of the machine would look like. These are big machines. They run on tracks. They've got trailing cables to power them. The front of the machines have these things. They're called rotors. They're kind of these triangular pieces. Depending on the miner, you might have 2 rotors or 4 rotors at the front. But you can see on these rotors, there's all these little thingies sticking out. Thingies is a technical term, right? So those are bits. And basically what happens is these rotors start to spin. They spin together, and then the bits, basically they start to spin, the borer advances into the rock or into the face, and those bits go into the face, into the rock, and start to grind the rock. And so they're spinning and grinding that rock. And then there's actually a conveyor belt in the throat of the machine. So the rock is falling to the ground and getting sucked up into the throat of the machine onto a conveyor. And then it's going to the back of the machine. So that's sort of the process of cutting at the active face. We also have these rotors, or these borers. So I mentioned some have 4 rotors. So these are wider in profile. Depending on the geology and where you are in the province, I guess, dictates whether you can use a 4-rotor or a 2-rotor machine. So the geology dictates how we mine. In often cases, it'd be awesome to mine wider or larger spaces, but we're sort of limited based on what our geology allows us to do. So these 4-rotor machines are used more in the southeastern area of the mine, where we have less clay seams and different ground conditions. Okay, so this is looking at what we would call the mining face. So in this case, the miner has mined ahead, and now we've backed off the face and we've taken a picture of the face. And this is what a very typical mining potash face in Saskatchewan would look like, especially in the Saskatoon area mines. So you can see, that sort of salmon pink color, that's very, very typical. And then these circular patterns you see, those are from the bits and the rotors spinning. So that's what the markings from the rotors and the bits leave behind. The most important thing to note on this picture are these darker seams. So these are those insolubles we were talking about. We call them clay seams, bands of clay. And these are very, very important in our mines because they're planes of weakness. So these are not stable seams. And so we actually have to mine them out. In a perfect world, if we could mine underneath them and not send these clays to the mill, because the mill doesn't want these, they want to get them out of the ore. It'd be great if we can mine under them. But the problem with those clay seams is they're very weak and they will fail. So we don't mine underneath them because we know that we'll end up with ground issues and our roof or back can cave in if we were to leave those seams above us. So it's very important for our operators to use these seams as a guide of where to mine. So they are actually paying attention to these seams as they mine along and are making sure that they stay along them and they're cutting them out. So this is the back of the machine. So in this case, the front rotors are up here. And so I mentioned that the ore will come up the machine and onto a conveyor. So here's the conveyor on the tail of the borer. So that ore is going to come up and dump off of that tail as the machine advances forward. Now, behind the machine, I know there's a lot going on in this photo, but behind the machine, so you can see here is the mining machine on the right. It would be cutting towards us. Behind the machine, you have what we call bridge conveyors. So these bridge conveyors are kind of like accordions. So there's a picture in sort of the left bottom here. they're kind of like accordions. They basically kind of like stack up against one another, and each one of those has a conveyor on it. So the ore comes off of the mining machine and dumps onto a conveyor on these bridges and kind of sequentially does that behind the machine. And the reason those bridges are stacked up is because that machine is pulling and advancing forward and also backing up at times. So the bridges, because they have that accordion effect, they can pull out or kind of shrink back and stack on top of each other. Basically, it allows for the mining machines or the borer to advance forward and then back up, advance forward and go at different angles, all while having those conveyors attached behind it. So then from these bridge conveyors, there's another conveyor called the panel conveyor behind them. So basically, once you cut the ore, you're just following or dumping the ore on a series of conveyors all the way back to the shaft. So out of the actual mining room, the ore then goes onto what we call mainline belts. And so again, just a conveyor belt, but these ones are special in that often they're wider and they're actually hung from the roof or the back of the mines. So we find in our potash mines that the roof is more stable. Not more stable, I shouldn't say. It is stable, but it stays in better condition than the floor. So often we'll have the floor buckling up or heaving, and that's often because of the clay seams in the floor as well. And so we actually mount these mainline conveyor belts onto the roof just for long-term just to keep them maintenance basically, so that we're not having to deal with ground conditions as the ore is traveling back to the shaft. So we have like tens of kilometers of travelways or belt lines for the ore to make its way back to the shaft. So essentially the ore gets onto these mainline belts and just dumps from one belt to the next all the way back and until it makes it to the shaft or the shaft area where we have bins. So this is a picture of a bin before the infrastructure was all in place. So this was a newly cut bin. So you can see this cylinder of rock cut out. So that's a bin. Depending on the site, there's different sizes and different setups of bins, but they'll range anywhere from holding 1,000 to 10,000 tons of rock. And basically the bins decouple the mining process from the surface operation. So essentially what happens is the ore can go all the way back to these bins. And let's say the mine has a down day, but the mill wants to keep running. If our bins are full, we can keep feeding the mill so that the mill doesn't have to shut down, even if we need to take a down day in the mine. So that's kind of what a bin looks like after we cut it. This is just intended to show what a bin would look like once you get all the infrastructure in. So you can see all the steel there. So basically the ore would come into the bin from the top and then come out at the bottom. And then from there, basically, from the underground bins, material is weighed underground by belts and then loaded into skips. And so the skips are what is actually inside of the shafts. Inside the production shaft. And so that's what's actually carrying the potash ore to surface. The skips move really fast. There's two generally, I should say, in a shaft. So basically every 115 seconds, one skip is getting loaded and one is dumping. So that blue thing is what is called a skip. So that would be what the potash muck is actually inside of when it comes up the shaft. And you can see down at the bottom, there's 4 people standing there just for a sense of scale. So these are quite big, quite large. Okay, so this is just a picture of a head frame. So basically this red long rectangle would represent that blue skip you saw in the other picture. And so there's these skips. They're basically on like a pulley system. So there's ropes, there's sheave wheels, and there's big hoist motors. So this right picture here is a picture of a motor, and so a hoist motor. So basically this skip would be dumping on surface, and you'd have another skip down below loading at potash level underground. And then once the one on the bottom's full and the one on surface is empty, they're just going to switch. So this one's going to go down and the other one's going to come up, and they're going to keep flip-flopping back and forth, bringing all that awesome mucked surface. So that is basically, oh, and then, sorry, I just have that little red circle to show this person here just to get a sense of the size of the hoist motor. So they're quite big when you're looking at those drums. Okay, so that's basically the process of potash mining, pretty high level, but essentially then we get the potash to surface, and from a mining perspective, we don't know what happens. It just goes into this black box we call the mill, and they process it. So Chantel's going to tell us what happens next.
Perfect. Thank you, Jenny. All right. What is potash processing? The magical black box. So really, it's how we get from this, the ore that Jenny worked so hard to get up onto surface, to this, our final product. So we kind of went over this, but just a little bit of a deep dive again. So the ore that comes up to surface, it's composed around, depending on the ore body or the mine site, 40% KCl. That's the potash part. That's the stuff we want. And then there's around 55% NaCl, the salt, and then 5% insolubles or clays, what have you. That's the stuff we don't want. And they're quite intermingled with each other, so it takes a little bit of work to actually get them separated. And just as a little bit of a side note, this is really a presentation discussing conventional mining where we get the ore from underground, bring it to the surface, and process it conventionally. But I will touch on crystallization, which is the premise of how solution mining works as well. So then our product, we call it muriate of potash or MOP, and it's composed primarily or 95% KCl, so that's the potash part, and sometimes more. So on the picture on the left, the red and the pink sort of coarser looking material, that's our granular potash, and that's used in mechanized farming and is often mixed with nitrogen and phosphorus and gets applied to fields. The one on the bottom left down here, that's called standard product, and that's typically sent to Southeast Asia, and it's hand broadcast onto rice fields, things like that. And then this white stuff up here, that can be up to over 99% purity, and it's an industrial grade product, and it's used in things like pharmaceuticals, the chemical industry, things like that. So it's really, really high grade. And there are other varieties, but these are just an example of some. And the reason this is darker and this one's lighter on the granular product is just it's from different ore bodies. So a little bit of a take on what the surface infrastructure looks like from the outside. So Jenny already talked about the production shaft, the access shaft, and then you can see from this production shaft, there's belt galleries that take the ore all the way to our processing buildings, our mill buildings right here. So this particular mine site has 2 mill buildings. They were built at different times, but depending on the facilities, there's often just one. And then after that, we have our product storage buildings. So these are the buildings where our product goes before it's loaded on to rail cars and shipped all over the world. So now let's take a look inside those buildings. So we're going to go through the mill process, and hopefully it's not too overwhelming or confusing. So again, once ore is on surface, we need to go to crushing and screening. So crushing and screening, really the goal of it is to liberate the KCl, the potash, the stuff we want, from the NaCl and insolubles or slimes, that's the stuff we don't want, without creating excessive fines, because the fines are really hard to recover and separate from each other. So this fun picture right here is called a QuemScan image. The purple represents the salt, the green represents the KCl, and the gray kind of represents the insolubles, probably anhydride or something in this picture. And you can see that at this size of particles, they're mostly liberated is the word we use. So the particles are separate from each other, though there are some that are still together, and we don't completely crush to liberate all the particles just because of the fines I talked about. So there's actually a regrind stage later on. And then we send that ore through to these crushers. This is a common type of crusher in our mills. It's called a cage mill, just as a size reduction. And then we use screens. There's various different varieties of screens, lots of newer ones from these ones, but they essentially all do the same thing. We screen out the material that's on size, and everything that's still oversized goes over the top and gets another round of crushing. So once we have our on-size material, it's important that we need to de-slime it, get rid of those insolubles. The slimes or insolubles are deleterious to the flotation process, so we have to remove them prior, or else we use excessive reagents and the process just isn't efficient. So it's really quite simple, but very important to get done right. So we primarily use cyclones or hydroseparators in the desliming process. So cyclones operation's quite simple. Really, it just uses centrifugal force, and the really fines and the brine goes out the overflow, and then the on-size product is higher in density or higher percent solids, and that goes out the underflow. We then use these hydroseparators, which use fluid dynamics essentially, and the really fine stuff, ends up being the clays, comes to the surface, and then the KCl that we want to recover goes to the underflow of these vessels. So after our ore is deslimed, we move on to flotation, which is really, I consider the heartbeat of our mill process. And flotation is a physical chemical process that's used to separate the desirable minerals from the gangue minerals. So it is quite simple, but anything that's quite simple has a million little nuances that go with it. In our slurry, as you noticed before, it's a wet process. The ore comes up dry, but we add brine to it once it gets into the mill. And so it's a wet process. So we add chemicals to this slurry that we've created, and they're called reagents. And that allows the KCl to selectively attach to bubbles and float to the surface. That's our concentrate, the stuff that we want. And then the salt is what we don't want, and it's actually just left behind at the bottom. So you can see this fun image of bubbles collecting KCl particles. And here's a variety of flotation machines. So this one on the left is a conventional mechanical flotation cell. They're used in potash mills all over the world. They were installed in the 1960s, 70s, 80s, pretty much unanimously. And they were great. They're easy to operate. They have good recoveries. But they do have lots of motors and lots of wear parts. So they're not perfect. And then later on, technology came, column flotation. And this doesn't show the entire column, but it's essentially just a really large circular vessel that allows potash to float. And columns are really good at floating fine material and allow us to get on grade. So that means the desired concentrate, like that 95% purity that we want in one single stage, while achieving really great recoveries, like into the mid to even high 90s at sometimes, depending on the material. And they've been added to our new mills. They're designed like that. And they're also added to the existing mills as cleaners, we call them. So they actually upgrade the concentrate grade of these mechanical cells. And then this thing is another type of column called a hydrofloat. And that really excels at recovering the coarsest particles. So ore bodies like Rocanville and Esterhazy have a higher liberation size. So the crystals where the NaCl and KCl are separate are actually much larger. So you can recover the coarser particles really well, though they're found at other sites. And I think it's really interesting to note that flotation vendors right now are selling coarse particle flotation vessels. Like it's a really brand new thing, but actually Nutrien or Potash Corp at the time, Rocanville, was the first ever site in the world to install a hydrofloat in 2008. So we've been using coarse particle flotation in potash for a very long time. And then this picture at the bottom is a picture taken recently with a camera that's actually in a flotation vessel that allows us to see the particles and bubble interactions on a real-time basis. So we can then adjust our reagents, our air rate, and how we operate the cells based on this image, which is then analyzed using computer vision to tell us all sorts of really important flotation parameters. And I think that's where we can get a lot of efficiency and recovery improvements by utilizing new technologies like this. Yes, there's new flotation vessels on the market, but can we do something to improve the operation of our existing equipment? All right. As promised, I'll also talk about crystallization, which is the other method of separating KCl from NaCl. So here's a picture of a crystallizer circuit. So it uses hot brine to recover potash. And they really excelled in the past before columns were very common, and they could recover that really fine stuff in our milling circuits. And then again, they're used to create super high purity product. So a little bit in depth on how crystallization works. So let's take an empty glass, add 100 grams of water to it, and then take some salt. Add some heat and then keep it saturated. Keep adding more as the heat increases. And then you can watch that saturation line. The water can absorb a little bit more salt as the temperature goes up. Now let's take KCl in water. Again, let's take our empty glass, add some water. Now we start pouring in KCl, add some heat, keep pouring in KCl to keep the solution saturated. And that saturation line actually looks quite different from the NaCl one. It's much steeper. You can continue to add more KCl as the water heats up. Okay, but what happens if we add them at the same time? Again, let's take our empty glass, add 100 grams of water, take our NaCl and KCl, start adding heat, and start pouring them in at the same time. Interesting. So as the temperature increases, the saturation of KCl or the saturation of NaCl actually decreases while KCl increases. So at 100 grams, this is the blue is the NaCl line, the water can take just under 15 grams of NaCl and around 22 and a half, say, grams of KCl. Now, the crystallizer circuit acts by decreasing the temperature throughout the bodies, we call them, but through the process, the temperature decreases. And what happens then is the solubility of salt actually increases. So the temperature decreases. Now the solution has the capacity to dissolve more NaCl, around 20 grams. And now the KCl line, it's much, much less. So as we decrease the temperature, we've actually precipitated out pure KCl from the solution. All right, so now that we have our KCl and NaCl separated, we go to the centrifuging and drying process. This is the section of the mill that I like to call the washing machine and dryer of the process, and it basically works like that. So this is a centrifuge from the outside, and this is an example of a centrifuge cut away from the inside. So we have our wet, slurry KCl and NaCl particles mixed in brine. We send it through the centrifuge, and it works like the spin cycle of your washing machine. Centrifugal forces go around, the screw pushes the really now dewatered particles through the end, and then all the brine comes out the other side. So then we have our damp particles or our damp clothes that we now need to throw into the dryer. So here's an example of two common dryers in potash mills. There are others, but these are kind of the most common, I would say. So this is a fluid bed dryer, and this is a video from inside a fluid bed dryer, and they have essentially plates or what have you on the bottom, and then air percolates up through the bottom and creates just this turbulent environment where the hot air and potash mix to dry it. And then this one's called a rotary dryer, and it's exactly like a clothes dryer at home. The potash comes in, it tumbles, hot air mixes with the potash, and out comes a dry product at the end. And I didn't specifically call it out here, but I did mention hot air. So all that hot air does pick up fine particulates of KCl, but we either scrub it or send it through electrostatic precipitators and cyclones to remove any of those particulates so we aren't releasing that to the environment after. Okay, so now that we have our dried product, we need to turn it into something that people actually want to buy. Compaction and sizing. So comes out of our dryers can be a wide variety of particle sizes depending on the crystals that we've collected. There can be very fine to quite coarse. We send them through these machines called compactors, and they're essentially two rolls that just squish all that material together to make a flake, and you can see some good examples of flake coming out here. And then we send that flake through crushers. Again, similar concept to the crushers and the crushing and screening circuit of the ore. Crush it up into smaller sizes. These are the screens we use for dry processing. And then eventually we get a super uniform product that looks like this using this process. And then there's, tight specifications, and we want to sell the exact right size to the farmer so it can blend well with the other fertilizer types. Before we go to loading, we'll also talk about tailings. So all that stuff that I talked about that we didn't want, we have to do something with that as well. And that's called tailings. So as Jenny mentioned, if you drive around Saskatoon or in the Southwest or by Regina, there's huge piles, typically red or pink piles of potash outside of our facilities. Those are known as our tailings piles. So that's primarily salt. And then we also have special areas to store the slimes or the insolubles as well. And in our Saskatchewan potash mines, we follow a zero liquid discharge policy. And what that means is we don't release any fresh water to environment. All the tailings get pumped out as a slurry. The solids settle on the pile, and then the brine essentially decants from that pile and is collected in brine ponds. And these brine ponds, we want to keep them at a constant level. And they collect any surface runoff or any rainwater from site so we don't contaminate the surrounding area as well. And then to keep them at a constant level, we actually deep well inject. So that means we pump the extra brine really deep underground in a safe place that we can actually store it. All right. Finally, loading and shipping. So once we've gone to all the work to separate the KCl from the NaCl, we've safely stored our tailings, then we load out that product onto rail cars. And across our sites, we load hundreds and hundreds of rail cars every single day. Those rail cars then make their way to the coast where they're loaded on ships and then transported to all the continents in the world. From there, they then maybe go on other rail cars, trucks, et cetera, until finally they reach the farm where they're destined for. And this is really no easy feat. The logistical challenges of transporting millions and millions of tons of potash from Saskatchewan, which is really the interior of the continent, all around the world, is quite amazing. You can also see in this middle picture, that's an example of one of the storage barns on site. So this site, this storage barn and the one next to it can hold up to 500,000 tons of potash, which is really an immense amount, but they do fill up, I promise, with the amount of product we produce. So that's why we're always working on loading these rail cars super efficiently and sending them away. And I think we finished right on time. Any questions for us?
You guys are great. You can put your hand up or you can talk in chat. Either way works for us for questions.
I
Oh,
don't
it's
have a
very quiet.
question,
Oh,
but I just want to say thank you for the very informative and very clear explanation of the process. I have much better understanding of it now. Thanks.
Awesome.
I have a really quick question, and
Yeah.
I'm not sure if anyone is well, I'm sure lots of people have asked. How did we first discover that we had potash a kilometer underground
It was from
in
oil and gas
Saskatchewan?
drilling. Yeah, people
Oh, okay.
from oil and
Interesting.
gas and putting drill holes all over the province and
Yeah,
realized, hey, there's potash there too. Yeah.
yeah. Nice. That's pretty awesome. And thank you, Jenny, also for co-presenting. I'm sorry that I missed you in the introduction.
That's okay. It was a bit of a sneak attack, so
It was a great sneak attack. You guys did a wonderful job.
Oh, I see there's questions in the chat, maybe.
I think there's a lot of thank yous.
There we go.
perfect.
Awesome. Well, I guess that's a good enough place to end. Thank you again for doing this wonderful presentation. That was probably one of the best potash presentations I've ever watched.
We'll take that.
Yeah. Thanks, everybody. I hope that everyone has a great rest of their day.
Awesome. Thanks so much, everyone, for listening.
Bye.
See you.